Welcome back. In today's lecture, we are going to deal with prodrugs. So, prodrugs, we have looked at them very briefly previously, and basically they are compounds which are derivatives of the active drug, and they themselves are actually inactive. So, that means that if I just administer them, they are going to be inactive. But inside the body, once they get into the body, then they are metabolized or they are converted by some enzymatic reaction pretty much to form the active drug. So, what this means is that it is like almost like a sleeping drug. So, it is by itself it is not active, but it is converted to an active form. So, if you see this concept, so prodrug would be inactive. That means, let us say I screen for an inhibitor of an enzyme, okay, and this prodrug itself it does not have any activity. Okay. But what happens is that it gets converted to the active drug, which can then inhibit the enzyme. Okay. So, the concept is that the reason we want to use this is because many times the drug itself might be a little bit toxic or may have many side effects, and so if you want to reduce the side effects, then you want to send the drug specifically to the area of interest where this enzyme is present. Okay. So, the concept is very straightforward, and there are many successful examples of prodrugs. So, implicit in this concept is the requirement of a metabolic enzyme. So, this metabolic enzyme, what it does is basically it converts the prodrug to the active drug. So, for us to design good prodrugs, we would need a very good knowledge of drug metabolism, and we also need to know in detail the enzymes that are involved in this process. So, once we have a good knowledge of this, so we have already studied extensively about ADME, which is basically absorption, distribution, metabolism and excretion. So, here the M, which is the metabolism, we have already studied it in detail. And so, once we know what are the enzymes that are involved and what are the type of reactions that are being formed, then we would be able to design a suitable prodrug, which then is designed to go into the body, get metabolized and form a active drug. Okay. So, here what we are doing is we are taking advantage of drug metabolism rather than addressing it as a or thinking about it as a problem. So, prodrugs have been designed by a variety of metabolic enzymes. So, there are perhaps about 20-30 examples of various metabolic enzymes. We will look at only a few of them. So, these metabolic enzymes, they should be enzymes which are able to turn over your prodrug into the active drug. The most common example is esters. So, here you have R, which is your drug. Let us say the drug has a free carboxylic acid. Then one could make a methyl ester or an ethyl ester of this molecule. Now, in the presence of esterase, okay, what you would expect would happen, it will form R C double bond O OH. Okay. So, here is the prodrug and here is the drug. Okay. Now, in terms of synthesis, what you would do is you would just do an esterification, right, to convert the carboxylic acid to the ester. So, this is a very straightforward examples, but you can also have other examples such as N-demethylation, where you have a N-methyl group, which we have already looked at, can be demethylated to form NH. You can also have decarboxylation, as in the case of L-dopa, and hydrolysis of amides. So, when you have amides, you can have hydrolysis, which is basically RCONH2, which will form RCOOH, right, and so on and so forth. So, all of these can be used, and of course, phosphates can also be hydrolyzed to give you the corresponding hydrolyzed derivative. So, there is a minor point here which we will look at in more detail later, which is that not all prodrugs are activated by metabolic enzymes. So, the definition of prodrug is that they are typically used by metabolic enzymes, but there are examples of using an external light source. So, what these do is that this is called as photodynamic therapy. So, here you have a drug which is attached to a molecule, and this molecule is actually what is known as photolabile. Okay. What this means is that the molecule is going to get cleaved under light. So, here is your light source, and if it is going to get cleaved, then it forms the drug and it will give out this attachment. Okay. So, this has again been used quite extensively, especially in cancer therapy, where you can localize the drug by using an external light source. We will look at this more in detail in the later part of this lecture. Okay. So, what we need to keep in mind when we are designing these prodrugs is that we need to ensure that the prodrug is effectively converted to the active drug once it is absorbed into the blood supply. Of course, we have to ensure that any groups that are cleaved are non-toxic. So, what this means is that let us say you have a prodrug in the form of drug and it has an appendage. Now, when it forms the actual drug, it is going to give away this appendage and this should be non-toxic. Okay. So, whatever that falls off, if it turns out to be toxic, then it becomes a huge problem, because then we are dealing with toxicity issues associated with the byproduct. Okay. So, now what we will do is we will study or we will look at in detail some of the various approaches to do to prodrugs. So, the first approach is to work on improving membrane permeability. Okay. So, we have already looked at many examples of how the various functional groups in a molecule that are going to help with membrane permeability, but there are certainly functional groups which do not help with this. So, basically you have, for example, a carboxylic acid which does not help with permeability because the lipid membrane is quite hydrophobic, and the carboxylic acid, which will probably exist as carboxylate, will not permeate the barrier. So, this results in a situation where you have a very nice drug, but it is not able to get across the cell membrane. So, in order to mask this, what people do is we convert it into an ester. Okay. So, this provides a temporary mask. So, you convert a carboxylic acid RCOOH to the corresponding ester. In this case, we can think about a methyl ester or an ethyl ester, and what it does is that because you have converted a highly polar group to a less polar group, the membrane permeability improves. Okay. Once it gets into the cell, then what happens is that esterase is going to cleave it and give you back the active carboxylic acid. So, this is one way in which we can temporarily mask an awkward functional group, which is obviously important for the target binding, but it is not able to get into the cell. So, this as we discussed, this carboxylic acid, there are many drugs with carboxylic acids and they are very good with ionic or hydrogen bonding interactions. And so, when we prevent this interaction from happening, the ester itself would not be very active, and therefore, it becomes useful. Okay. So, the very fact that an ionizable group may prevent it from crossing a fatty cell membrane is something that has led to a number of esters. So, we can now make a number of esters which have various permeabilities and various stabilities. Okay. So, now for example, you can look here is the this molecule called as enalapril, which is actually a prodrug of the antihypertensive agent enalaprillate. Okay. So, here is the molecule where R equals H is the active drug, and this is the ethyl ester which will produce ethanol as a byproduct, and these are cleaved by esterases in the bloodstream. So, what it helps with is that it helps with getting the molecule cross the membrane, and once it gets into the bloodstream, it can then get cleaved by esterases to produce the active compound. Now, not all esters are equally efficient in getting hydrolyzed. So, which we can very well imagine would be a function of the leaving group ability. So, if you see the way in which the mechanism for ester hydrolysis occurs, you have perhaps a hydroxide of some sort coming in here, kicking this out, coming back in and giving you this O minus through the tetrahedral intermediate. So, it will give you this tetrahedral intermediate, which then collapses to kick out RO minus to give you the carboxylic acid, right. Now, if you had a serine in the active site doing the same function, then you would get the same product and RO minus. Okay. Now, because this tetrahedral intermediate collapse is very important, the nature of the leaving group here can be changed. So, for example, if you have an electron withdrawing group such as CH2 CF3, then O CH2 CF3 versus O CH2 CH3, the fluorinated compound is going to be a much better leaving group, and therefore, it will hydrolyze much faster. Okay. Similarly, you can make other variety of leaving groups and you can tune the release rates. Okay. So, the inductive effect of the CF3 is going to make this ester a far better hydrolyzing. Each of the fluorines are going to have a inductive effect, right. So, this is going to be far better in getting hydrolyzed when compared to the ethyl ester. Now, of course, if you make it too reactive, then what happens is that in the acidic conditions in the stomach, it can get hydrolyzed almost spontaneously, or even in the alkaline conditions that are present in the intestine, it can get hydrolyzed, and that defeats the purpose. So, therefore, you need to make the ester to be appropriately stable, so that it should be hydrolyzed at the right rate in the right place, so that it can form the active drug at the right area. So, another example of a ester, that is a carboxylic acid, is the cyclopropane carboxylic acid ester. So, if you were to make, imagine that your drug has an alcohol, so then you could make a cyclopropane carboxylic acid ester and can again undergo hydrolysis to give you cyclopropane carboxylic acid and ROH. Okay. So, now let us look at this a little bit in detail. So, you can also have a conjugated double bond. So, for example, you can make C double bond O, OR, and what this does is that because of the interaction of the pi system, you can now change the way in which the carboxylic acid is going to hydrolyze. So, you would get OH plus the product as ROH. Okay. So, similarly, if you compare the conjugated alkene and the cyclopropane, in the cyclopropane, the sigma bonds of the cyclopropane are oriented correctly to allow for hyperconjugative interaction. So, if you see, so hyperconjugative interaction can occur, and these are the sigma bonds, and this allows for the conjugation to occur, hyperconjugation to occur, and it is going to stabilize the carboxylic acid. And of course, we know that the hyperconjugative effect is donation to the anti-bonding pi orbital of the carbonyl. So, you have a C double bond O and you have a anti-bonding pi star, and here the sigma bond donates to the pi star of the carbonyl and stabilizes it. Okay. The next way in which you can do this to make prodrugs is to use N-methylated prodrugs. So, N-demethylation we have looked at previously is actually a very common reaction that occurs, and it would produce a polar amine. Okay. So, what we can do is we actually methylate it so that you can reduce the polarity, and this improves the membrane permeability. So, if you see for example, if you have a membrane and if you have NH2 plus, right, which is going to be possibly equilibrating with RNH2. Now, if you convert sorry, this is NH3 plus and then RNH2, and now you can imagine RNH2 being converted to RNHMe, okay, and the position of this equilibrium would be quite different. Similarly, if you had a pyrrole type of ring or a pyrrolidine type of ring, if it has an NH, instead of that if you have NMe, so here this lone pair is more available and it is going to get protonated, whereas the methylated one is not going to be very well protonated due to sterics. So, there are several examples of this which are known. So, what we would do is we would purposefully convert an amine into the methylated amine, so that reduces the polarity and improves the membrane permeability. So, the example that we are going to look at is this molecule, which is hexabarbitone, whose structure is shown here, and it has an amine or an amide here, and this is hexa barbitone with the methyl group, and now it undergoes metabolism to give you the active derivative So, if you see here, the methyl group has been removed and you actually get a NH. Okay. So, this is an example of how demethylation can be used for generating a active drug. Another major way for prodrug approach is to look at the Trojan horse approach. So, one of the major problems with delivering molecules is the permeability of this molecule, because we have spent a lot of time in designing molecules which can actually interact with hydrogen bonds or ionic interactions and all that, and all of these are quite polar. So, now for these to get across the membrane, it is going to be difficult. However, there are proteins which are known as transport proteins, which we have looked at previously, and these are responsible for carrying amino acids into the cell. So, one way to work around the problem of membrane permeability is to use these transport proteins. So, here these transport proteins are actually located inside the membrane, and they have pretty much structures like these, and these allow for transport of amino acids. Okay. So, the concept would be to be able to use these transport proteins to get across your drug. Okay. So, the example that we are looking here is levodopa. So, levodopa's structure is shown here. We have looked at it previously. It resembles a naturally occurring amino acid, except that it has two hydroxyl groups, and this is levodopa. And here this is actually inside the cell, it gets converted to dopamine, which we have already looked at previously. Okay, so this is dopamine, right. This is a drug that is used for the treatment of Parkinson's disease, and in this disease, one of the symptoms of this disease is a deficiency of the neurotransmitter in the brain. So, the idea would be to deliver this neurotransmitter to the brain, right. So, levodopa, as you can see, has a amine as well as a carboxylic acid. So, what one could design this prodrug to be is to actually access the amino acid transporters and get it across the cell. Once it gets into the cell, it gets decarboxylated and produces the active dopamine. Okay. Levodopa is even more polar and seems like an unlikely prodrug, but because of its resemblance to an amino acid, it is recognized by transport proteins and it gets it across. Okay. And as we discussed earlier, once it is in the brain, a decarboxylase removes the acid group and generates the active dopamine. The next concept is to be able to prolong the drug activity. Okay. So, sometimes prodrugs are designed to be converted very slowly into the active drug. Here the idea is that you do not want, for example, the drug to be present at very high concentrations at all times. So, you want to be able to generate the drug in a slow fashion. So, let us say we plot the concentration of a drug versus time. So, without a prodrug, what happens is that you will have a spike in the drug concentration and then it goes down, right. But imagine if you want to generate this drug for a long time, so then you could mask it as a prodrug so that it generates the active drug over a longer period of time, right. So, this is one of the important approaches that are used in prodrugs. So, the example we are going to look at is the 6-mercaptopurine. So, the structure of 6-mercaptopurine is the following. You have a heterocyclic ring, N double bond, and as the name mercapto suggests, it should have a sulfur. Okay, so, this is 6-mercaptopurine, it has a hydrogen over here, and this is a drug that is used to suppress the immune response. So, when you have a transplantation that occurs, the donor's organ is given to the acceptor's organ, and once we have the donor graft that sits inside the body of the acceptor, then the person's immune system is going to recognize it as a foreign substance and try to get rid of it. So, in order to protect it, there are immunosuppressants that are given, and 6-mercaptopurine is one of the immunosuppressants. But the problem with this molecule is that it gets eliminated very quickly in the body. So, we want to be able to protect it from metabolism, so that it is generated very slowly over a period of time, so that the rejection rate goes down. In order to do this, what we do is we convert this molecule into a prodrug. Okay. So, this azathioprine is a prodrug. Okay. So, the concept here is that if you see the structure of mercaptopurine is over here, you protect it with this nitroimidazole molecule. This nitroimidazole molecule is very interesting because it has a site which is highly electron deficient. Okay. So, this site, which is as drawn here separately, has a almost like a Michael acceptor kind of system. Okay. So, as you already are all familiar with, Michael reaction is addition of a nucleophile to an alpha beta unsaturated ester, ketone and so on. Here your nucleophile, which is in this case a thiol, attacks here, and you can push arrows to get an intermediate like that. Now, when the intermediate collapses, it has a choice of kicking out glutathione or it kicks out mercaptopurine. So, when it kicks out mercaptopurine is the actual drug. So, by allowing for this molecule to be triggered or activated by glutathione, what we achieve is a more sustained activity. Now, what we can do is that we can alter the rate of reaction with glutathione, and then you can actually slow down the release further or increase the release. So, if you put a strongly electron withdrawing group on the imidazole ring, so what we can do is we can actually change the electronics on this ring, so that we can tune the rate of reaction with glutathione. So, if we put a strongly electron withdrawing group on this imidazole ring, then you can increase the rate of reaction, whereas if you put an electron donating group, then you would suppress the rate of reaction. So, based on this, one can sort of figure out how the conversion of the inactive compound to the active compound can be altered. Now, there is another commonly used drug which is called as Valium, and this is a drug that is used as a sedative, and it is believed that these sedatives such as Valium and Librium are actually prodrugs, and they are metabolized by demethylation to form this active molecule. So, Nordazepam itself has been used as a sedative, but what happens is that it loses activity very quickly because it is metabolized and excreted. So, by masking this molecule as Valium, what happens is that this N-methyl can get cleaved and produce the active compound. So, then what happens is that because it depends on the rate of N-methyl demethylation, then the activity of this drug can be prolonged, so to lead to sustained action. Another approach to maintain a sustained level of the drug is to put in a very lipophilic group on the drug. So, this can be done by ionic interaction. So, what happens is that the drug will actually, because of its close association with this lipophilic group, is going to get stored in the fat tissue. So, because it is stored in the fat tissue, it is going to release the drug in a very slow and steady manner into the bloodstream. And so, this is one of the ways in which you can sustain the release of the drug. Okay. So, the example here that we are going to look at is this anti-malarial drug cycloguanil. So, here what we do is that this compound is actually associated with this bis carboxylate shown here, and this forms an ionic interaction, and this ionic interaction with a large lipophilic group results in a very slow dissociation of the molecule into the bloodstream. And so, you can actually regulate the amount of drug that is released into the bloodstream. Similarly, you can also use lipophilic esters. So, here is an example of a 9 carbon appendage which you can use as a carboxylate to your active drug. So, the fluphenazine is given intramuscularly, and because it has such a large lipophilic group on it, it diffuses very slowly from the fat tissue into the bloodstream. And then once it gets to the bloodstream, it is actually rapidly hydrolyzed to produce the active drug. Another major task in prodrugs, or major success with prodrugs, is to reduce the drug toxicity and side effects. So, for example, we all know that salicylic acid is an excellent painkiller, and once it is consumed, it causes gastric bleeding. Okay. So, it is actually converted to aspirin, which is acetyl salicylic acid, which is basically a prodrug. So, this is aspirin. Okay. And so, what happens is that aspirin is actually cleaved within the cell, perhaps by esterases, and gives you the active salicylic acid. Another way example of this molecule is propylaldehyde. So, the structure of this molecule is as shown here, which is NMe. It has a propagyl group over here. Okay. So, what happens is that this molecule gets cleaved to produce the propargylaldehyde, okay, and it is converted to propylaldehyde by enzymes in the liver. So, this is one molecule that is given in the treatment of alcoholism. So, as you know, alcoholism is a situation where somebody who is unable to control the level of alcohol that they consume. So, they are addicted to alcohol, and so what happens is that this molecule is given to people, and what happens is that it creates a very bad taste, and therefore, it does not allow people to, or does not help with people to consume alcohol. So, it prevents alcohol consumption. Okay. Another classic example of masking drugs is cyclophosphamide. We have already looked at it previously, but the concept is very important. So, here you have DNA alkylating agent that is masked in the form of a phosphanamide, and once it gets cleaved, it forms the active drug. So, here is the position that is susceptible to oxidation, and you form. Okay, so, now you can think about this going out here and this picking up a proton and giving you this molecule, and then subsequent cleavage will give you the final right, and acrolein is the byproduct. I will encourage you to push arrows and find the mechanism, and so therefore, it produces the active DNA alkylating agent, and this is used in the treatment of cancer. Another example which we have looked at previously are these antiviral drugs such as acyclovir. So, acyclovir is a mechanism based inhibitor. So, you have create this situation where this molecule will go and get incorporated into DNA, but will not allow for replication to occur. So, here is the molecule acyclovir, right. So, what it does is that since it has to be working on viruses, the viral enzyme converts this into an active form, and then only then it can go into and incorporate into the nucleic acid to prevent further replication.